lesson 15 tonight. What do we know about evolution? And this is going to be the beginning of where we kind of start breaking away from the structure set forth by the book. I don't expect us to get past this page tonight. Actually, yes. If we do get past this page, then the rest of it will actually go pretty quickly because I don't have much of a plan for the rest of it. But I think I have enough to talk about on page 61 in your book that we're going to have a good night tonight. So, to start with, so this chapter is about learning the theory of evolution. I've kind of taught you guys the basics of the theory of evolution already, about how natural selection has been shown to cause populations to change over time, and but that doesn't actually create new species. That simply kicks out old species and quite possibly causes them to go extinct if the natural selection takes place worldwide. And then I talked about how the evolutionary answer to that is that every now and then there is a genetic mutation that changes the nature of the population, and most of the time mutations are bad and it just causes the thing to die. But there's the rare occasion where a mutation is actually beneficial to an organism, and so then that new organism that is better adapted to its environment will outcompete the lesser versions of it, and after a few generations, or many generations, whatever, after some time, all of the old stuff will have died out, or at least greatly reduced in population, and this new species of animal will rise to dominate, and so that is how evolution takes place. That is what people who believe in what I call Darwinian evolution believe. So we talked about how there's two different definitions of evolution. This is from a long time ago. Talked about how evolution is a thing that we observe, that populations change over time, and then the other side of it is evolution is a story of the history of the world, where this thing that we observe in the present is used to explain the past. And so that is the theory of evolution that we're dealing with. We have no issue with the actual observation of populations changing over time. That happens. And it fits with the Bible too. What we take issue with is the story that is told of the earth, of life on earth coming about through evolution. Basically, at one point in the extreme distant past, billions of years ago, there was a single-celled organism that came to life somehow and then started reproducing, started dividing. And from there, the forces of natural selection and mutation took over, and the organism became better and better adapted to living on Earth, creating many, many different species and phyla and all of the other levels on the taxonomic hierarchy and stuff. And that's how the world came about today. I would draw pictures, but it takes too long, and it should be review for you guys because we've already gone over that. So we're going to revisit the theory of evolution, and we're going to talk about some of the assumptions behind it, because that is where we can see that it really falls apart. It's definitely not a biblical Christian idea, but really it's not even a good scientific idea. And when you realize the assumptions that are being made to make it work, you will also realize that it's baloney. So that's what we're going to talk about tonight. Evolutionary assumptions. Don't write anything above the top speech balloons. You're going to want to save space probably to take notes on the bottom too. What assumptions does an evolutionary worldview make about the existence of God? If you believe in evolution, what are you assuming about the existence of God?
That the 7 days didn't happen?
The 7 days didn't happen, but that's an event in history. But we're talking big picture, the existence of God. If you believe in Darwinian evolution, what does that say about the existence of God? Probably that God doesn't exist, right? Or at least he doesn't need to exist. There are going to be some who claim to be Christian and then also believe in Darwinian evolution, and they will say, well, I believe God exists, just that, this is how he created the world. And that causes theological issues, like why would God create a world where death reigns? But we're not going to get into that. Generally, those who believe in the theory of evolution believe that God either doesn't exist or they have kind of a deist view. Do you guys remember what the deists believe about God? The deists believe that there is a God, but what do they say about him?
Do they talk about what they left it? Like left the earth? Or is that something else?
Yeah, I think you're on the right track. That you're saying that deists believe that God made the universe and then left. Yeah. Yeah, that's what deists believe. That basically they feel like they need God to explain something about the universe, and where it comes from. But they also basically say that that God's not here anymore. Did I remember to push record on the phone? Could you check real quick, Zoe, and just see if it's recording?
It's working.
Okay, good. Thank you. Just had one of those moments. Okay, how about the next speech balloon there, the other blue one? What assumptions does an evolutionary worldview make about the natural and supernatural realm? Natural meaning like what we can observe in the world around us, and supernatural being anything having to do with spirits, angels, God, stuff like that. Maybe write some of these on the board, but this is not really what I'm going to focus on. So, what do you think an atheist believes about angels?
But they're not real.
They're not real? Okay, what do you think an atheist believes about your soul, aside from your body? Your spirit?
That it dies with your body?
Right, so really then, is it even a separate thing from your body?
No. Yes.
It's not. Right, so really anything about the supernatural, that is anything that is beyond the world that we can see and touch and experience for ourselves, doesn't exist. There is no supernatural. Okay, and that is an extremely convenient assumption for them to make, because we have no reason to think that the world that we see is all that exists. But if you make this assumption that there's nothing that we can't see, because that's what the natural world is like, the universe, so it includes not only the earth and the trees and the things that we typically call nature, but also the other planets and the stars and the universe itself. That's all the natural world. And that's all the world that we can see. Maybe we don't have good enough telescopes to see all of it, but in theory we can see it. We could get to it if we could travel faster than light, or light, or use wormholes or whatever. That's all stuff in the natural universe. Whereas everybody agrees, Christians and atheists alike, that God exists outside of the natural world. That we cannot find God unless God allows himself to be found. Of course, the atheist would just say that we'll never find God because he doesn't exist. Whereas we would say, well, God exists. God does exist, but he exists outside of the natural world. So the evolutionary assumption is generally that there is nothing outside of the natural world. And that's an awful convenient thing to believe, because that means that everything that exists is something that I can see or experience or discover for myself. So yeah, those are, I don't really have a lot to say about those. I think they're pretty part and parcel to the atheistic worldview. What I want to talk about first is the age of the earth. What do you think the evolutionary worldview has to say about the age of the earth? How old is the earth?
Don't they say it's only like a couple 100 years old?
100 years old?
Or no,
million.
Now the Bible says the earth is roughly 6,000 years old.
Like, don't they say it's like a really long time?
Yeah,
Like,
yeah, the
really long?
dinosaurs died 65 million years ago, right? And dinosaurs are really complex organisms. So if the dinosaurs died 65 million years ago, then that means that life must have existed for millions, if not billions of years before that. And of course, life only randomly arose after billions of years of non-life existing. So yeah, the evolutionary assumption, and I'm going to change colors here because this is important. The Earth and the universe, but we're going to focus on the Earth. The Earth must be billions of years old. This is a serious weakness in the theory of evolution because it does not work if the Earth is young. If the Earth is young, then evolution simply cannot happen. And I'll get to why in just a moment. But for now, recognize that if we can show scientifically that the Earth is young, then that is a major blow against the theory of evolution. And so it should be no surprise then that evolutionists fight very hard to make sure that we know, or that we hear that the Earth is old. Almost any scientific text you read that has to do with life is going to shoehorn somewhere into the discussion that life evolved over millions of years. Try it sometime. Anything, I mean, even most of the stuff geared at kids has like a requisite millions of years thing somewhere in it. I can't remember the last time I read a science book to one of my children that it was not made by Christians. And it did not include that the Earth is millions of years old. They always get that in there somehow. Earth is millions of years old. Earth is billions of years old. They speak of things that happened, 1.4 billion years ago, as if it's just a fact, as if we just know that. That's what happened 1.4 billion years ago. And they say it so often and so confidently that that people are led to believe that, okay, we just know that the Earth is billions of years old. But in fact, we don't know that. And in even more fact, there is a lot more evidence saying that the Earth is not millions of years old, that it's quite a bit younger. Now, why must the Earth be billions of years old? Let's dig into that question a little bit. The Earth must be billions of years old because of an assumption called uniformitarianism. That one is worth writing down. Uniformitarianism. There it is. It's a really long word. But you can see if you break it down, it's got the word uniform in there, so like everything is the same, and that's kind of the idea. Uniformitarianism is hard to define formally, but the belief is basically things, and Stacy Lung used this word last week, if you remember that. Things are the way they've always been. So, for example, now let me give a good example. The Grand Canyon has a river running through it, right? And we can measure, thanks to our precise instruments, we can measure that the Grand Canyon is widening the river, the river at the bottom of the Grand Canyon is getting wider at a rate of like, a 1/10 of an inch per year. I'm making that number up, but that's the idea. Very precise measurement, but we can make it. And every year, some years are better than others, but every year the width of the river gets bigger by about 1/10 of an inch, let's say. That's what we observe. So the observation, here's a timeline. Let's put this one in red, so it's going to be a bad observation. Here's our timeline, right? And so in the year 1990, we observed the river to be, so wide. And then in 1991, we observed it to be wider. In 92, 93, whatever, and we got. Let's just pretend like these marks lead us across 30 years. So these marks represent 30 years. And in these 30 years, we see that it changes by 0.1 inch per year. Okay? So now we have an actual observation, and the observation is that the river gets 0.1 inches deeper, wider, whatever it is, per year. What uniformitarianism says is that this rate that we have found here, if I were to make a graph here over time, so this is 1 year, and this is 0.1 inches. So the rate looks like this, right? If you've done any algebra in school, this kind of graph might look familiar, otherwise don't worry about it. But it's basically saying that we measure in 30 years, the rate is 0.1 inches per year. So what we're gonna do then is we're gonna go back. We're gonna say, okay, the Grand Canyon is a mile deep, it's 1 mile deep. So how long did it take that river to carve a 1 mile deep canyon?
Oh my god.
Well, that's just math. Okay, it's hard math for those of you who aren't math people. But you plug it into a computer and it spits out an answer right away, you know. You just use the rate and work backwards. Say, okay, we know the river is carving out, 0.1 inches deeper every year. So if the canyon's a mile deep, then all you have to do is convert a mile into inches and divide it by 0.1, and that's how many years it's been since the river started carving the canyon, right? The problem is that we don't know that this is 0.1 inches per year. That is an assumption made based on uniformitarianism, that things are the way they've always been. So if we measure this rate in this tiny little span of time, then we are assuming that it's the same rate all throughout history. And that's an assumption that we cannot verify. We don't know that. And really, there's no reason to think that. I mean, are there not floods? Are there not other events? Could the river not have been going a different route for a while and then moved? Rivers moving is a well-documented phenomenon that happens sometimes. There are so many things that could have happened that we can conceive of in our imaginations, let alone all of the actual things that happened. And to say that we can confidently speak to the rate of the distant past because we made just a few measurements in half a lifetime is absurd. But that is the uniformitarian assumption, is that if we measure something now, we can safely assume that that is the way it has always been. And that is not a safe assumption. Another example, and this deals with a question from the last lesson we did that we didn't quite get to because I wanted to focus on Noah's flood, and that is radiometric dating. Who's ever heard of radiometric dating? You remember my stupid joke that I made last week? Radiometric dating is when you go to the radio and you say, hey baby, you want to go out to some supper? Yeah, that's radio. Yeah, you remember it now. I don't remember anything about it, but Pastor made a stupid joke about it, so I remember that. Whatever, that's why I make stupid jokes, so that you'll remember. So radiometric dating is complicated, but you need to understand it because that comes up a lot. Scientists say, oh, we know that these rocks are 1 billion years old because radiometric dating says so. We sent it to the lab, and they did radiometric dating and determined that these rocks are 1 billion years old. So we know that they are because the lab said so. In order to understand radiometric dating, you have to understand radioactivity. Does anybody think they know anything at all about radioactivity? Yeah, this is tough, but I have to tell it to you to understand why radiometric dating is not what it's cracked up to be. It does come down to this principle though, so I'm also going to be teaching this principle a second time. So if you didn't get it the first time, maybe you'll get it this time. Radiometric dating is when you have an atom. You guys know what atoms are?
Wait, is that tree thing you really conveyed? No, that's not that.
Nope, not that. I haven't taught this in class before. You have atoms, and they're made of protons and neutrons in a nucleus. Does this sound familiar to anybody? Yeah, protons have a positive charge, right? And the neutrons have a negative charge. And then you got your electrons buzzing around here, but we're not going to focus on the electrons. When people talk about nuclear stuff, nuclear energy or nuclear power, what they are referring to is the nucleus of the atom. You know about that the protons and neutrons and stuff are the nucleus of the atom. By the way, this is not drawn to scale. And if this were drawn to scale with this kind of electron cloud, you wouldn't even be able to see the nucleus. It'd be so tiny. And that's, of course, atoms are tiny in and of themselves. But anyway, when the nucleus of an atom sticks together pretty well, but as the atom gets bigger and that nucleus gets bigger, it doesn't stick together as well. Everything going all right there? Got some weird glances happening. The middle part of the atom, as the atom gets bigger, the middle part doesn't stick together very well. And sometimes what happens is it gets too darn big, and the atom says, "All right, I can't even anymore." And so it'll get rid of something. It might get rid of a neutron, for example, or it might get rid of a. Actually, I don't think it gets rid of neutrons. What does it get rid of? I don't remember. There's alpha, beta, and gamma radiation, and I can't remember right now what. But the important thing is when it gets rid of a proton. So sometimes it'll get rid of a proton. It'll just be like, bye-bye proton. But here's a problem. If you know the periodic table of elements,
Yeah.
you do. Okay, I wasn't expecting that actually.
Yeah.
Okay,
You
so
have to do over punishment.
do you remember what determines what an element is?
Okay, wait, say it again.
Okay, so like you have an element on the periodic table of elements. How do you know what element it is?
Because of the number.
And what does the number mean?
The amount of
Something.
protons.
Protons, yes. The number of protons in an atom determines what it is. So, if the atom kicks out a proton, it actually becomes a different element, right?
Yes.
And as it turns out, one of the most well-known radioactive elements is uranium. And uranium is unstable, which means every now and then the atom will kick out a proton or a neutron or a gamma ray or something like that. It'll kick stuff out, and when it kicks that stuff out, it's called radiation. And you know radiation's bad for your health, right? You don't want to be eating uranium in your cereal or whatever.
Oh.
But when it kicks out a proton in particular, it decays into something else. It's no longer uranium, because uranium has a certain number of protons. I forget what it is. I really should have studied this stuff before class today, but I was busy doing other things. So whatever number of protons uranium has, if it kicks out a proton, it is no longer uranium. It becomes something else. And this happens several times, and every time it happens, it changes. And sometimes it kicks out a proton, and sometimes it kicks out a gamma ray or whatever. But eventually, it decays into lead. This is the chemical symbol for lead, like what they used to put in pencils and paint and pipes and everything else. That was a terrible idea because lead is toxic.
Wait, lead is toxic?
Yes.
Yes, never eat lead.
That's why didn't they switch it in pencils to
Yeah, pencils nowadays have graphite in them.
Yeah.
Oh, I
They-
thought it was still
They
lead.
call it the lead because that's tradition, but
Traditional.
tradition. Yeah, but it's and it used to be lead, but nowadays it is graphite. And similarly, paint is made with latex, where it used to be made with lead, and fuel is unleaded fuel. So we are still paying for the sins of the lead-ridden past. But as toxic as it is, one thing that lead is not is radioactive. Lead is a big atom, but it's not too big. So lead will just sit around forever and just be lead. It's not going to decay anymore. Uranium will decay. And it turns out that there is a way to measure how much time it takes for a chunk of uranium to decay into a chunk of lead. In fact, I'm going to redraw the lead here in green to help illustrate this next point. So uranium decays into lead. It actually decays into a whole bunch of things and eventually ends with lead. But that's not important. What's important is that they measure this decay in what's called a half-life. So say you have 1 gram of uranium, right? After a half-life, however long that is, Anyone familiar with the video game Half-Life?
Oh, I've heard of it.
Okay, yeah, the name is based on this concept. After a half-life, the sample that you have will now be 5 grams of lead and 5 grams of uranium. Only it doesn't look like a frickin' Pokeball. That was a really bad example. Instead, it looks like a sample of uranium with chunks of lead in it.
Oh.
Yeah, more like this, because the decay doesn't happen like from top to bottom or whatever. It's just random atoms. Every now and then, an atom of uranium decays into lead, and if you have a sample of uranium and give it a half-life of time, which it turns out the measured half-life of uranium is like millions of years. I forget how long it is. And that's based on uniformitarianism. You know, we measure the half-life for 1 year, or we measure the decay rate for 1 year, and then we extrapolate that out to millions of years. But in any case, in this case, we have 0.5 grams of lead, even though it doesn't look like it, and 0.5 grams of uranium. And, okay, so you understand that, and you can Google the half-life of uranium. I don't know what it is. Let's call it call it a billion years.
A billion? Ooh,
Yeah.
that's a long time. You know how much
It
a
is,
billion
it's-
years is?
I do,
A
yes, it's 10
billion.
to the power of 9.
Yeah.
You know, I'm not even going to write a billion years there because I don't want to write things that I don't know are true. But it's a long time. Does anybody have a phone? You want to just Google the half-life of uranium?
Amazon, that's your,
There you go.
what you got?
Okay. So then after another half-life, this won't be down to full lead. Instead, after another half-life, this will be down, come on,
A half-life of what?
uranium.
$4.5 billion.
4.5
Oh
billion.
my
Okay, there we go.
gosh.
So I'll throw that out there. Now, obviously, nobody has sat around and measured the rate of uranium decay for 4.5 billion years. What we do is we measure it for 1 year or 30 years or however long we want, and then we say, okay, if it decayed this tiny little bit in 1 year, then it must take 4.5 billion years for the whole sample to decay. If you do another half-life, you don't get 0 though. Instead, you get 75 grams of lead, and or 0.75 grams of lead, and 0.25 grams of uranium. So the sample will look a little more like this, perhaps, where it's predominantly lead, but it's got quite a bit of uranium left in it. So, this is how radioactive decay works. Now, how do we use dating with this? So here's what we find. Suppose you find, remember, so science is all about measuring the present. It's not all about this, but historical science, and I'll get into what that means in a moment. Historical science is all about looking at the present and trying to figure out what happened in the past that led to that present. Okay? So, if in the present, let's say you find a sample of lead, it's almost entirely lead, but there are little specks of uranium in this sample. And you take it back to the lab and you measure it very precisely, which we don't doubt our measuring tools. Our measuring tools can do this. And you find that it is 99% lead and 1% uranium.
Is that UR?
Uranium is just U.
Oh, what's
Yep.
UR?
Not uranium. Ur.
Oh.
So let's suppose this is what we find. And we look at this rock and we say, how old is this rock? Or how old is this sample of lead? And in reality, there's going to be other crap in with it too.
It's
But
gonna say
keep it
it's
simple.
like 400 billion.
Yeah, well, what we're going to do is we're going to follow the half-life back. We're going to be like, okay, so 4.5 billion years ago, this would have been 2% uranium. And 4.5 billion years before that, this would have been 4% uranium. and 4.5 billion years before that. So I'm realizing now my numbers are totally unrealistic. The sample that you would find would be mostly uranium with a little bit of lead. But by using this thing, actually that's a good example. I'm going to keep this up here because I'm sure there do exist samples in nature like this, and
probably in space.
maybe on Earth. So here's the deal: is when you ask how old is this rock, all you have to do is we can actually do this right now. So 1% uranium. Okay, so 4.5. We'll do number of half-lives. Okay.
So it's basically 99 times 4.5.
Not exactly, no, because it doubles every time. So 4.5 billion years ago, it would have been 2% uranium. And 4.5 billion years before that, it would be 4%. And 4.5 billion years before that, it would be 8%, 16%, 32%, 64%, and some fraction of a half-life for 100%. Obviously, you got to stop at 100. So what is that? 1, 2, 3. Oh, of course, it's 6. We'll call it 6. Keep the math easy. 6 times 4.5 billion is 27 billion. Yes, that's correct. 27 billion years old. So 27 billion years ago. Now let's write this down here. I'm putting it in red because it's wrong. 27 billion years ago. Billion. I'm just going to put YA for years ago. This sample was 100% uranium.
That's crazy.
Okay. Why is that crazy?
Because the Earth isn't here yet.
I just proved it though. I found this sample, and we just went back in time with the half-life and figured out how old it is.
How do you know the half-life?
So without resorting to that's stupid, it can't be true. What questions can we ask? Braden started asking a question. What did you say, Braden?
How do you know the half-life is real?
Okay, so assumption number 1.
Oh.
We're going to call this the decay rate. Rate is constant.
How do we know something did speed up the process?
Okay, yeah, that fits in there as well. But one thing that you kind of hinted at there that I'll add here is that there are no contaminants.
What's contaminants mean?
Something that contaminates your sample. So
They
suppose
found some that were contaminated.
yeah, so suppose like a billion years ago, this thing was melted, and a bunch of extra lead got into it. Then suddenly that would change our number because our present amount of lead would be much higher if it got contaminated by lead. And if it's 27 billion years old, there was probably an opportunity or two for some extra contaminants to get in there. Yeah. So we have to assume that this sample is uncontaminated in its entire life. Because if anything gets added to it or taken from it, then that changes the measured rate, right? And there's one more assumption. This is the biggest one of all, and I'm surprised you guys haven't spotted it yet.
Hold on.
And there's one more problem with this thought process that.
Oh, I know.
What is it?
They say the Earth wasn't even made before.
No. This is just something I made up. I don't know if any examples like this exist in nature. We're just assuming that we found one and seeing where it takes us. No, the third one is initial. I don't know how to make this simpler. Sorry. Initial composition is known. Who says that this used to be pure uranium?
Yeah.
Yeah. So this whole date here is based on the assumption that every single atom of lead in this sample used to be uranium.
Yeah.
We don't know that. All 3 of these assumptions are faulty, and all 3 of these assumptions must be true in order for radiometric dating to be valid. Radiometric dating assumptions. This is worth writing down. These 3 things here. Okay. Now the decay rate is constant, even though we've only measured half-lives for like 100 years. Suddenly we know that they don't change after 4.5 billion years. that there are no contaminants in any given sample that we have, and that we know what the sample was at the beginning, whatever the heck the beginning was. Remember when we talked about how when God created the world, he did not make a bunch of babies, right? He made a mature world. So we talked about how if you cut down a tree in the Garden of Eden, there would probably be rings inside of it. And if you thought that every ring represented 1 year, then you might think that those trees were like 40 years old or whatever. But in reality, they were 3 days old. So the same principle applies here. If God created this chunk of uranium that had a bunch of lead in it already, then even when that thing was 0 days old, radiometric dating would make it look like it was billions of years old. So if you don't know the initial composition, which we don't, obviously, we can't know what this thing was like at the beginning of its life, then the radiometric dating is meaningless.
Okay, somewhat off topic, not really.
Okay.
What if, like, there was something that, like, sped up the processes? Like, if they look into trees and, like, they date the world off of, like, the trees,
Okay.
like, what if something, like, made that different? Like, 1 year it was super wet, so things grew faster, but 1 year, like, things, like, weren't good, so things didn't grow.
Well, we try not to think about that because we believe in uniformitarianism. But you're absolutely right. This is one of the reasons why uniformitarianism is bad.
Yeah.
I should
Good
add
job, guys.
that here.
I know, Bruce.
This is bad. I should say this is wrong. Bad implies that it's the opposite of good, whereas I'm just trying to say that it's not valid, it's not true. But the uniformitarian assumption is found everywhere in evolutionary thinking because it's all they've got. If you believe that everything in the world has to be measurable, then we have to have some way to measure the past. And you say, well, how can we measure the past? We don't have a time machine. Well, we can measure the present, and we can assume that the past is just like the present. I believe Stacy Lung summed up uniformitarianism saying the present is the key to the past. And so if we make this massive and very wrong assumption, then we can figure out the past. But of course, this massive and very wrong assumption is, well, massive and very wrong. But it's all we got. And for the evolutionist, that's enough. As long as we got something to believe in, I'll believe it. Yeah, it's extremely flawed logic. Do you guys feel like you understand this, or would you like a simpler example?
I get it.
Okay. The other thing I want to talk about is what's that?
Yeah, ask me what I said.
It sounded like gibberish.
Oh, she said I get it.
Like
Yeah.
English?
Okay, the other thing I want to talk about is that yellow speech balloon on page 61. I don't like people making a big deal out of evolution being a theory and not a fact. You hear that all the time. Evolution's a theory, not a fact. A theory is a well-founded scientific belief, and to say evolution is a theory, not a fact, makes it sound stupid, but really it doesn't hold much water scientifically. What I like to talk about instead is the difference between historical science and operational science. I'm gonna write that on the board. So we're gonna talk about science. Science. Okay, so there are two kinds of science. I'm gonna put operational science first. Operational and historical science. If this book had been written by people who understand science better, I think that yellow speech balloon would have this distinction rather than theories and laws. Because theories and laws are just man-made titles for things. But here's the two kinds of science, and they're both good, but they're also both limited. So let's look at operational science. Operational science is something that can be controlled. So, for example, operational science says that hydrogen gas and oxygen gas react together in the presence of heat to produce water. I know, crazy, right? H2O, that's how it comes from. And we know this because we can do it in a controlled environment. We can isolate hydrogen gas and isolate oxygen gas, and then we can mix them together in a chamber with no other gases in it, and we can add heat to it, and we can measure how much heat it takes to catalyze the reaction, and then boom, it generates a lot of heat once it starts. So it's a self-propagating reaction, and it ends up with water.
Wait, do people actually make water from that?
It's not a practical way to make water. Like, you know, it's hard to extract hydrogen. It's hard to isolate hydrogen gas.
But have people done it?
Yes, they have. They've done it in a laboratory, in a controlled environment. Another thing is that it's repeatable. So, suppose I'm the guy who discovered that hydrogen gas reacts with oxygen gas to make water. I'd be like, hey, you can make water by reacting hydrogen and oxygen. And another scientist would be like, no way, man, are you serious? I'm like, yeah, man, try it. And so he goes to his lab, and he isolates hydrogen gas and isolates oxygen gas and mixes them together, heats them up, and water. And he's like, wow, I just repeated your experiment. And this is how operational science works, is we control the environment and we repeat the experiment. Let me change colors for the downsides of operational science.
Is it safe to drink?
Yes, it's just water. It's
Water?
literal, it's pure water. That's how water is made.
That's
Oh,
all
you
water
guys gotta
today?
take a chemistry class.
I don't know if I'm gonna take that.
Alright,
I don't
anyway.
get it.
Yeah, I mean, there might be some hydrogen gas that you want to let bubble out or something, but I don't think hydrogen gas is toxic.
Well, if it makes water.
Anything's toxic if it's high enough concentration. Anyway, downsides of operational science is kind of the same as the upsides. It has to be controlled. So, for example, psychological studies. If I want to know, just psychological studies. If I want to know the effects of the color red on people's emotions, you know, suppose
Angry.
suppose I take 100 people and I measure their brain waves, I measure their you know, brain image, whatever you want to call it, after they see the color red. I'll get some results, but it's not very well controlled because people are complicated. Maybe this person had a traumatic experience involving blood in their childhood. So when they see red, they're reminded of that very specific trauma. Whereas this other person's colorblind, so to them the red is just the same as green, and it's like, well, okay, whatever, you know, that's the color of the grass, I guess. So it's very difficult to control an experiment. I'll write that they're difficult or expensive in many cases.
I see grass. I see the sky.
A major limit of operational science is that it cannot measure the past. Cannot measure the past. Right.
Okay.
So, the ocean is filled with water, and we can react hydrogen and oxygen to make water. Does that mean that the ocean used to be hydrogen and oxygen?
Yeah.
No.
Oh, dang it.
Pretty solid.
It does not mean that. There are other ways to get water, and of course, eventually you have to get to the ultimate cause, whatever that is.
Then
So-
how did it not used to be?
Operational science cannot measure the past. We're going to leave it at that. Operational
My
science
brain
cannot measure the
is-
past. Historical science. What historical science does is it. I should have written the definition at the top. Oh well. It examines the present. To learn. No, learn isn't the right word. What? Something wrong with my butt?
I don't know.
You don't know? Thank you, Tyson. To figure out the past. Okay, so an example of historical science would be you walk into a room and there's water all over the floor, and you look up at the ceiling and you see water dripping from the ceiling onto the floor, and you as a scientist say, I bet the water on the floor came from the ceiling.
Well, that's
Alright.
not-
That's historical science, yeah, and you're probably right. There's a lot of merit to historical science, but you don't know. Maybe some idiot spilled water on the floor and went to go get a mop, and then we just happen to have a very unfortunate leak right in that spot. And so really, the leak, you saw the very first drop of that leak, and it just happened to leak into that puddle that was already there. Yeah, that's a crazy story, and it's probably not true, but the fact that we can't know for sure that it's not true, or that it's true or not, is a limitation. Historical science, the biggest problem is open to bias. I'll put that. Open to bias. I mean, the leak in the puddle is pretty obvious, but one example would be the Earth is made up of rock layers, sedimentary rock layers that were deposited by water, apparently. Somebody who believes the Earth is billions of years old would say, well, that must have been deposited over billions of years. Whereas somebody who believes in a worldwide flood relatively recently would say, well, those rock layers were deposited by the flood. So we're both seeing the same evidence, but our bias is dictating how we interpret that evidence. And as for measuring the past, historical science still cannot measure the past. What's up, everybody? It's your boy Pastor Larson here. So my battery kind of died and cut off the last 5 minutes of class last night. So I'm here today, which is actually tomorrow from when this lecture began, to finish off what I was talking about. So I've recopied what I erased from the board at the end of class here. And the point that I want to make here is that even though it is called historical science, and the whole purpose of historical science is to figure out, history, the fact remains that we cannot measure the past. Not with operational science, not with historical science. If you have a fossil, you have a fossil in the present. Now the fossil is pretty strong evidence of what happened in the past, but the story that you try to construct to explain how that fossil came to its present state is just that. It's a story. And the story might take into account lots of other evidence. Indeed, I'm not trying to poo-poo historical science here. It is a legitimate field of study. It actually contains many legitimate fields of study. Archaeology, paleontology, forensic science, all kinds of stuff falls under this. But we have to recognize its limits. A lot of critics of the Christian and creationist movements, they like to tell us that we are anti-science, and we're not. We have utmost respect for both kinds of science, and I mean, if there's a third kind, I'd be willing to accommodate it or whatever. We recognize the value in finding tangible evidence and using that evidence to construct ideas, theories, if you will, about the nature of reality, but we also recognize the limits of science. And so when the word of man, as dictated by science, comes into conflict with the word of God, it's not like we have to say, we have to turn off our brains and listen to the Bible over against science. No, we just need to come up with a better story of how the present day evidence came to exist in the present day. And the Bible tells us the history of Earth, even things that archaeology and anthropology and paleontology have not yet figured out. And from that answer, we can construct a better theory to explain the present, and it takes into account what we know to be true about the past, and it very easily accommodates all of the evidence that we have. Because when something is true, then everything else that is true is evidence for it. It's just a matter of understanding how that can be. So I believe that's about all that I wanted to say about historical and operational science and the differences thereupon. So to sum up today's lesson here. Let me grab my book here. Remember that the theory of evolution requires that the Earth be very old. And it requires that chiefly because the rate of change that we see in animal and plants, in living populations, the rate of change that we actually observe in the present is simply way too small for the Earth to be young. If the Earth is young, then that means that all of the modern species of animals were made more or less the way that they actually appear today. Of course, there's still some 6,000 years of change that could have taken place, which is a long time, and so we would expect to see some considerable differences, but it's not like cats and dogs share a common ancestor or something like that. There just isn't enough time unless you stretch it out so that the Earth is actually billions of years old. And uniformitarianism is that long name for the philosophy that evolutionists embrace, which says that we can understand the past by measuring the present. So, for example, if the Grand Canyon gets 1/10 of an inch deeper every year, then we can extrapolate that backward and figure out when the Grand Canyon started getting deep, sometime in the distant past. And uniformitarianism is baloney. It's not based on any actual factual evidence. It just is a philosophy that you have to embrace if you want to go and say that the Earth is so ridiculously old as they do. So those are kind of the two pillars that I wanted to break down today in our combating of evolutionary thought. Thanks a lot for sticking around to the end, and to see you off, I have here a song that I'm going to play for you. Oh!